A hash function is any function that can be used to map data of arbitrary size to data of fixed size, with slight differences in input data producing very big differences in output data. The values returned by a hash function are called hash values, hash codes, hash sums, or simply hashes. One practical use is a data structure called a hash table. Hash functions are also frequently used to accelerate table or database lookup, detecting duplicated records in a large file, and finding similar stretches in DNA sequences. They are also useful in cryptography. A cryptographic hash function allows one to easily verify that some input data matches a stored hash value, but hard to reconstruct the data from the hash alone. This principle is used by the PGP algorithm for data validation and by many password checking systems. Hash functions are related to checksums, check digits, fingerprints, randomization functions, error-correcting codes, and ciphers. Although these concepts overlap to some extent, each has its own uses and requirements and is designed and optimized differently. The HashKeeper database maintained by the American National Drug Intelligence Center, for instance, is more aptly described as a catalog of file fingerprints than of hash values. Uses: hash tables. Hash functions are primarily used in hash tables, to quickly locate a data record given its search key. Specifically, the hash function is used to map the search key to an index. The index gives the place in the hash table where the corresponding record should be stored. Hash tables, in turn, are used to implement associative arrays and dynamic sets. Typically, the domain of a hash function is larger than its range, and so it will map several different keys to the same index. Therefore, each slot of a hash table is associated with a set of records, rather than a single record. For this reason, each slot of a hash table is often called a bucket, and hash values are also called bucket indices. Thus, the hash function only hints at the record's location, it tells where one should start looking for it. Still, in a half-full table, a good hash function will typically narrow the search down to only one or two entries. Caches. Hash functions are also used to build caches for large data sets stored in slow media. A cache is generally simpler than a hashed search table, since any collision can be resolved by discarding or writing back the older of the two colliding items. This is also used in file comparison, Bloom filters. Hash functions are an essential ingredient of the Bloom filter, a space-efficient probabilistic data structure that is used to test whether an element is a member of a set. Finding duplicate records. When storing records in a large unsorted file, one may use a hash function to map each record to an index into a table T, and collect in each bucket T, I, a list of the numbers of all records with the same hash value I. Once the table is complete, any two duplicate records will end up in the same bucket. The duplicates can then be found by scanning every bucket T, I, which contains two or more members, fetching those records, and comparing them. With a table of appropriate size, this method is likely to be much faster than any alternative approach. Protecting data. A hash value can be used to uniquely identify secret information. This requires that the hash function is collision-resistant, which means that it is very hard to find data that generate the same hash value. These functions are categorized into cryptographic hash functions and provably secure hash functions. Functions in the second category are the most secure but also too slow for most practical purposes. Collision resistance is accomplished in part by generating very large hash values. For example, SHA-1, one of the most widely used cryptographic hash functions, generates 160-bit values. Finding similar records. Hash functions can also be used to locate table records whose key is similar, but not identical, to a given key. Or pairs of records in a large file which have similar keys. For that purpose, one needs a hash function that maps similar keys to hash values that differ by at most m, where m is a small integer. If one builds a table T of all record numbers, using such a hash function, then similar records will end up in the same bucket, or in nearby buckets. Then one need only check the records in each bucket T, I, against those in buckets T, I plus K, where k ranges between AM and AM. This class includes the so-called acoustic fingerprint algorithms, that are used to locate similar-sounding entries in large collection of audio files. For this application, the hash function must be as insensitive as possible to data capture or transmission errors, and to trivial changes such as timing and volume changes, compression, etc. Finding similar substrings, the same techniques can be used to find equal or similar stretches in a large collection of strings, such as a document repository or a genomic database. In this case, the input strings are broken into many small pieces, and a hash function is used to detect potentially equal pieces, as above. The Rabin-Eurocarp algorithm is a relatively fast string searching algorithm that works in O(n) time on average. It is based on the use of hashing to compare strings. Geometric hashing, this principle is widely used in computer graphics, computational geometry and many other disciplines, to solve many proximity problems in the plane or in three-dimensional space, such as finding closest pairs in a set of points, similar shapes in a list of shapes, similar images in an image database, and so on. In these applications, the set of all inputs is some sort of metric space, and the hashing function can be interpreted as a partition of that space into a grid of cells. The table is often an array with two or more indices, and the hash function returns an index tuple. This special case of hashing is known as geometric hashing or the grid method. Geometric hashing is also used in telecommunications to encode and compress multi-dimensional signals. Standard uses of hashing in cryptography. Some standard applications that employ hash functions include authentication, message integrity, message fingerprinting, data corruption detection, and digital signature efficiency. Properties: good hash functions, in the original sense of the term, are usually required to satisfy certain properties listed below. The exact requirements are dependent on the application. For example, a hash function well suited to indexing data will probably be a poor choice for a cryptographic hash function. Determinism: a hash procedure must be deterministic, meaning that for a given input value it must always generate the same hash value. In other words, it must be a function of the data to be hashed, in the mathematical sense of the term. This requirement excludes hash functions that depend on external variable parameters, such as pseudo-random number generators or the time of day. It also excludes functions that depend on the memory address of the object being hashed, because that address may change during execution, although sometimes rehashing of the item is possible. Uniformity: a good hash function should map the expected inputs as evenly as possible over its output range. That is, every hash value in the output range should be generated with roughly the same probability. The reason for this last requirement is that the cost of hashing-based methods goes up sharply as the number of collisions pairs of inputs that are mapped to the same hash value increases. Basically, if some hash values are more likely to occur than others, a larger fraction of the lookup operations will have to search through a larger set of colliding table entries. Note that this criterion only requires the value to be uniformly distributed, not random in any sense. A good randomizing function is generally a good choice as a hash function, but the converse need not be true. Hash tables often contain only a small subset of the valid inputs. For instance, a club membership list may contain only 100 or so member names, out of the very large set of all possible names. In these cases, the uniformity criterion should hold for almost all typical subsets of entries that may be found in the table, not just for the global set of all possible entries. In other words, if a typical set of M records is hashed to N table slots, the probability of a bucket receiving many more than Mn records should be vanishingly small. In particular, if M is less than N, very few buckets should have more than one or two records. When testing a hash function, the uniformity of the distribution of hash values can be evaluated by the chi-squared test. Defined range: it is often desirable that the output of a hash function have fixed size. If, for example, the output is constrained to 32-bit integer values, the hash values can be used to index into an array. Such hashing is commonly used to accelerate data searches. On the other hand, Cryptographic hash functions produce much larger hash values, in order to ensure the computational complexity of brute force inversion. For example, SHA-1, one of the most widely used cryptographic hash functions, produces a 160-bit value. Producing fixed-length output from variable-length input can be accomplished by breaking the input data into chunks of specific size. Hash functions used for data searches use some arithmetic expression which iteratively processes chunks of the input to produce the hash value. In cryptographic hash functions, these chunks are processed by a one-way compression function, with the last chunk being padded if necessary. In this case, their size, which is called block size, is much bigger than the size of the hash value. For example, in SHA-1, the hash value is 160 bits and the block size 512 bits. Variable range. In many applications, the range of hash values may be different for each run of the program, or may change along the same run. In those situations, one needs a hash function which takes two parameters the input data z, and the number n of allowed hash values. A common solution is to compute a fixed hash function with a very large range, divide the result by n, and use the division's remainder. If n is itself a power of 2, this can be done by bit masking and bit shifting. When this approach is used, the hash function must be chosen so that the result has fairly uniform distribution between 0 and now AA1, for any value of n that may occur in the application. Depending on the function, the remainder may be uniform only for certain values of n, for example odd or prime numbers. We can allow the table size n to not be a power of 2 and still not have to perform any remainder or division operation, as these computations are sometimes costly. For example, let n be significantly less than 2b. Consider a pseudo-random number generator function p, key, that is uniform on the interval 0, 2 bar AA1. A hash function uniform on the interval 0, n1, is np, key, /2b. We can replace the division by a right bit shift, np, key, b. Variable range with minimal movement. When the hash function is used to store values in a hash table that outlives the run of the program, and the hash table needs to be expanded or shrunk, the hash table is referred to as a dynamic hash table. A hash function that will relocate the minimum number of records when the table is where z is the key being hashed and n is the number of allowed hash value is such that h, z, na plus a1, equals h, z, n, with probability close to n slash, na plus a1. Linear hashing and spiral storage are examples of dynamic hash functions that execute in constant time but relax the property of uniformity to achieve the minimal movement property. Extendable hashing uses a dynamic hash function that requires space proportional to n to compute the hash function, and it becomes a function of the previous keys that have been inserted. Several algorithms that preserve the uniformity property but require time proportional to n to compute the value of h, z, n, have been invented. Data normalization. In some applications, the input data may contain features that are irrelevant for comparison purposes. For example, when looking up a personal name, it may be desirable to ignore the distinction between upper and lowercase letters. For such data, one must use a hash function that is compatible with the data equivalence criterion being used, that is, any two inputs that are considered equivalent must yield the same hash value. This can be accomplished by normalizing the input before hashing it, as by uppercasing all letters. Continuity. A hash function that is used to search for similar data must be as continuous as possible. Two inputs that differ by a little should be mapped to equal or nearly equal hash values. Note that continuity is usually considered a fatal flaw for checksums, cryptographic hash functions, and other related concepts. Continuity is desirable for hash functions only in some applications, such as hash tables used in nearest neighbor search. Non-invertible. In cryptographic applications, hash functions are typically expected to be non-invertible, meaning that it is not possible to reconstruct the input data mix from its hash value h, x, alone without spending great amounts of computing time. Hash function algorithms. For most types of hashing functions, the choice of the function depends strongly on the nature of the input data, and their probability distribution in the intended application. Trivial hash function: if the datum to be hashed is small enough, one can use the datum itself as the hashed value. The cost of computing this trivial hash function is effectively zero. This hash function is perfect, as it maps each input to a distinct hash value. The meaning of small enough depends on the size of the type that is used as the hashed value. For example, in Java, the hash code is a 32-bit integer. Thus the 32-bit integer and 32-bit floating point float objects can simply use the value directly. Whereas the 64-bit integer long and 64-bit floating point double cannot use this method. Other types of data can also use this perfect hashing scheme. For example, when mapping character strings between upper and lower case, one can use the binary encoding of each character, interpreted as an integer, to index a table that gives the alternative form of that character. If each character is stored in 8 bits, the table has only 28 equals 256 entries. In the case of Unicode characters, the table would have 17A, 216 equals 1,114,112 entries. The same technique can be used to map 2-letter country codes like US, or ZAR to country names, 5-digit zip codes like 13,083 to city names, etc. Invalid data values may be left undefined in the table, or mapped to some appropriate null value. Perfect hashing. A hash function that is injected via that is, maps each valid input to a different hash value is said to be perfect. With such a function one can directly locate the desired entry in a hash table, without any additional searching. Minimal perfect hashing. A perfect hash function for n keys is said to be minimal if its range consists of n consecutive integers, usually from 0 to -1. Besides providing single-step lookup, a minimal perfect hash function also yields a compact hash table, without any vacant slots. Minimal perfect hash functions are much harder to find than perfect ones with a wider range. Hashing uniformly distributed data: if the inputs are bounded length strings and each input may independently occur with uniform probability, then a hash function needs to map roughly the same number of inputs to each hash value. For instance, suppose that each input is an integer z in the range 0 to -1, and the output must be an integer h in the range 0 to -1, where n is much larger than n. Then the hash function could be h equals z mod n, or h equals n, or many other formulas. H equals Z mod n was used in many of the original random number generators, but was found to have a number of issues. One of which is that as n approaches n, this function becomes less and less uniform. Hashing data with other distributions: these simple formulas will not do if the input values are not equally likely, or are not independent. For instance, most patrons of a supermarket will live in the same geographic area, so their telephone numbers are likely to begin with the same 3 to 4 digits. In that case, if m is 10,000 or so, the division formula m, which depends mainly on the leading digits, will generate a lot of collisions. Whereas the remainder formula z mod m, which is quite sensitive to the trailing digits, may still yield a fairly even distribution. Hashing variable length data: when the data values are long character strings such as personal names, web page addresses, or mail messages their distribution is usually very uneven, with complicated dependencies. For example, text in any natural language has highly non-uniform distributions of characters, and character pairs, very characteristic of the language. For such data, it is prudent to use a hash function that depends on all characters of the string and depends on each character in a different way. In cryptographic hash functions, a Merkle-Damg-NRD construction is usually used. In general, the scheme for hashing such data is to break the inputs into a sequence of small units and combine all the units B1, B2, B, M, sequentially, as follows. SO. Initialize the state. For k in 1, 2. M do scan the input data units, SAF, S, B, K. Combine data unit K into the state. Return G, S, N, extract the hash value from the state. This schema is also used in many text checksum and fingerprint algorithms. The state variable S may be a 32 or 64-bit unsigned integer. In that case, SO can be 0, and G, S, N, can be just S mod n. The best choice of F is a complex issue and depends on the nature of the data. If the units B, K, are single bits, then F, S, B, could be, for instance. If high bit, S, equals 0 then, return 2S plus B, else, return P. Here high bit, S, denotes the most significant bit of S. The asterisk operator denotes unsigned integer multiplication with lost overflow. Is the bitewise exclusive or operation applied to words? And P is a suitable fixed word. Special-purpose hash functions. In many cases, one can design a special-purpose hash function that yields many fewer collisions than a good general-purpose hash function. For example, suppose that the input data are file names such as FILE0000CHK, FILE0001CHK, FILE0002CHK, etc., with mostly sequential numbers. For such data, a function that extracts the numeric part K of the file name and returns K mod n would be nearly optimal. Needless to say, a function that is exceptionally good for a specific kind of data may have dismal performance on data with different distribution. Rolling hash. In some applications, such as substring search, one must compute a hash function h for every k-character substring of a given n-character string T, where k is a fixed integer, and n is k. The straightforward solution, which is to extract every such substring s of T and compute h, s, separately, requires a number of operations proportional to car n. However, with the proper choice of h, one can use the technique of rolling hash to compute all those hashes with an effort proportional to car plus a n. Universal hashing. A universal hashing scheme is a randomized algorithm that selects a hashing function h among a family of such functions, in such a way that the probability of a collision of any two distinct keys is 1/n, where n is the number of distinct hash values d0 independently of the two keys. Universal hashing ensures that the hash function application will behave as well as if it were using a random function, for any distribution of the input data. It will however have more collisions than perfect hashing, and may require more operations than a special-purpose hash function. See also unique permutation hashing. Hashing with checksum functions. One can adapt certain checksum or fingerprinting algorithms for use as hash functions. Some of those algorithms will map arbitrary long-string data Z, with any typical real-world distribution no matter how non-uniform and dependent to a 32-bit or 64-bit string, from which one can extract a hash value in 0 through null AA1. This method may produce a sufficiently uniform distribution of hash values, as long as the hash range size n is small compared to the range of the checksum or fingerprint function. However, some checksums fare poorly in the avalanche test, which may be a concern in some applications. In particular, the popular 32 Costa Rican colons checksum provides only 16 bits that are usable for hashing. Moreover, each bit of the input has a deterministic effect on each bit of the 32 Costa Rican colons, that is, one can tell without looking at the rest of the input, which bits of the output will flip if the input bit is flipped. So care must be taken to use all 32 bits when computing the hash from the checksum. Hashing with cryptographic hash functions. Some cryptographic hash functions, such as SHA-1, have even stronger uniformity guarantees than checksums or fingerprints, and thus can provide very good general-purpose hashing functions. In ordinary applications, this advantage may be too small to offset their much higher cost. However, this method can provide uniformly distributed hashes even when the keys are chosen by a malicious agent. This feature may help to protect services against denial-of-service attacks. Hashing by nonlinear table lookup. Tables of random numbers can provide high-quality nonlinear functions to be used as hash functions or for other purposes such as cryptography. the key to be hashed would be split into 8-bit parts and each part will be used as an index for the nonlinear table. The table values will be added by arithmetic or XOR addition to the hash output value. Because the table is just 1024 bytes in size, it will fit into the cache of modern microprocessors and allow for very fast execution of the hashing algorithm. As the table value is on average much longer than 8 bits, 1 bit of input will affect nearly all output bits. This is different from multiplicative hash functions where higher value input bits do not affect lower value output bits. This algorithm has proven to be very fast and of high quality for hashing purposes. Efficient hashing of strings. Modern microprocessors will allow for much faster processing, if 8-bit character strings are not hashed by processing one character at a time, but by interpreting the string as an array of 32-bit or 64-bit integers and hashing accumulating these wide-word integer values by means of arithmetic operations. The remaining characters of the string which are smaller than the word length of the CPU must be handled differently. This approach has proven to speed up hash code generation by a factor of 5 or more on modern microprocessors of a word size of 64-bit. Another approach is to convert strings to a 32 or 64-bit numeric value and then apply a hash function. One method that avoids the problem of strings having great similarity is to use a cyclic redundancy check of the string to compute a 32 or 64-bit value. While it is possible that two different strings will have the same CRC, the likelihood is very small and only requires that one check the actual string found to determine whether one has an exact match. CRCs will be different for strings such as AI and AB. Although CRC codes can be used as hash values, they are not cryptographically secure since they are not collision resistant. Locality-sensitive hashing. Locality-sensitive hashing is a method of performing probabilistic dimension reduction of high-dimensional data. The basic idea is to hash the input items so that similar items are mapped to the same buckets with high probability. This is different from the conventional hash functions, such as those used in cryptography, as in this case the goal is to maximize the probability of collision of similar items rather than to avoid collisions. One example of LSH is min-hash algorithm used for finding similar documents. Let H be a hash function that maps the members of A and B to distinct integers, and for any set S to find min, S, to be the member X of S with a minimum value of H, X. Then min, A, equals min, B, exactly when the minimum hash value of the union A of B lies in the intersection AA copyright B. Therefore, PR, min, A, equals min, B, equals J, A, B, where J is jacket index. In other words, if R is a random variable that is 1 when min, A, equals min, B, and 0 otherwise, then R is an unbiased estimator of J, A, B, although it has too high a variance to be useful on its own. The idea of the min-hash scheme is to reduce the variance by averaging together several variables constructed in the same way. Origins of the term hash comes by way of analogy with its non-technical meaning, to chop and mix. Indeed, typical hash functions, like the mod operation, chop the input domain into many subdomains that get mixed into the output range to improve the uniformity of the key distribution. Donald Knuth notes that Hans-Peter Lunn of IBM appears to have been the first to use the concept, in a memo dated January 1953, and that Robert Morris used the term in a survey paper in CACM which elevated the term from technical jargon to formal terminology. List of hash functions. NIST hash function competition, Bernstein hash, Fowler-Nolvo hash function, Jenkins hash function, Pearson hashing, Zobrist hashing. See also, Computer Science Portal. References. External links, Hash Functions and Block Ciphers by Bob Jenkins, The Goulburn Hashing Function by Meher Patel, Hash Function Construction for Textual and Geometrical Data Retrieval Latest Trends on Computers, Volume 2, ppA 483 489, CSEC Conference, Corfu, 2010.